previous lecture, we set up the Schrodinger equation for spherically symmetric systems and then argued and showed that the angular momentum is conserved for such systems, and therefore, we can find the because of h L square being 0, h L being 0, but L I L j not being equal to 0 for I not equal to j, we can find the eigenfunctions that are simultaneous eigenfunctions, or what I will say is common eigenfunctions for h L square and only one component of the angular momentum. And what we will do is, because of the simplicity, we will choose the Lz component for eigen functions. Why is so? Because Lz has a very simple form, h cross over I d by d phi. And we also found that the Hamiltonian can be written as minus h cross square over 2 m r square partial r square partial with respect to r plus L square over 2 m r square plus V r. And L square contains only theta and phi. L square contains only theta and phi derivatives. And therefore, one can anticipate that the eigenfunctions of H, which are simultaneous eigenfunctions of L square, are going to be such that the eigenfunctions of L square are basically irrespective of what V r is, because this V r out here in the Hamiltonian does not really contain any theta and phi terms. So, therefore, L square is going to be independent of that, L square eigenfunction should be independent of that. So, what we are going to focus on in this lecture are the eigenfunctions of L and therefore, L square and Lz operators. So, let us do that. First, the simplest thing, 1, eigenfunctions of Lz. So, these are going to be, suppose these are, let me write this as q phi. Then I am going to have Lz q phi equals some eigenvalue, let us write it some eigenvalue lambda q phi. This is h cross over I dq over d phi is going to be equal to lambda q, and therefore, I have dq over d phi minus I lambda over h cross q equals 0. The solutions for this is very simple. So, solution for q is therefore q phi is equal to e raised to I lambda over h cross phi, some constant in front, the normalization constant. How do we find These are the eigenfunctions. So, eigenfunctions of Lz operator are some constant c e raised to I lambda over h cross phi. We are yet to find lambda, but these are the eigenfunctions. What about lambda? So, recall that eigenvalues are determined by some boundary condition. Now, what is the boundary condition in this case? This is, if I take the x y plane and let phi go around once. So, phi equals 2 pi, we will see is equivalent to phi equals 0, and therefore, the wave function q phi plus 2 pi should be the same as wave function q phi. Otherwise, the wave function will keep changing as you go around once, twice, thrice, and therefore, I should have e raised to I lambda over h cross phi times e raised to I 2 pi lambda over h cross equals e raised to I lambda over h cross phi. This term cancels, and I have e raised to I 2 pi lambda over h cross equals 1, and this implies immediately that lambda is going to be some m h cross, where m is an integer or 0, plus minus 1, plus minus 2, and so on. So, what we learn is that the eigenvalues of Lz are m h cross, with m being 0, plus minus 1, plus minus 2, and so on, and the eigenfunctions are e raised to I. Now, I can write this as m phi. Eigenfunctions are e raised to I m phi, and if I normalize the eigenfunctions, they will be normalized over the range of phi, which is 0 to 2 pi, and I am going to have mod q square d phi should be equal to 1. So, if I take q to be c e raised to I m phi, I will find that c comes out to be 1 over root 2 pi. So, my eigenfunctions, normalized eigenfunctions q phi for Lz are 1 over square root of 2 pi e raised to I m phi, m equals 0, plus minus 1, and so on. So, what we found is that Lz has eigenfunctions 1 over root 2 pi e raised to I m phi, m equals 0, plus minus 1, and so on, and eigenvalues are m h cross, again m equals 0, plus minus 1, and so on. What about eigenvalues for Lx and Ly? Suppose I were to solve Lx times some q, right, which will be a function of theta and phi both, equals lambda q theta and phi. Now, you see these direction z is chosen arbitrarily. Direction z is chosen arbitrarily. So, z is chosen arbitrarily. So, if it is chosen arbitrarily, the next time this axis could be the z axis. So, eigenvalues should not really depend on the direction. So, eigenvalues for Lx and Ly will also be same, mh cross, m equals 0 plus minus 1 and so on, except that the eigenfunctions would be different because now the operator is different, but the eigenvalues cannot depend. What value Lz takes or a component takes is the same. The only thing that happens is now, because Lx Ly is not equal to 0 or Lx Lz is not equal to 0, therefore, I cannot find simultaneous eigenfunctions of Lx, Ly and Lz. So, I choose only one component Lz, and then I cannot, that cannot be the eigenfunction. So, e raised to I m phi 1 over root 2 pi cannot be the simultaneous eigenfunction of Lx and Ly. So, we can choose only one, all right, and that eigenvalue is this. Now, what about L square? L square Lz turns out to be 0. So, I can find simultaneous eigenfunctions of L square and Lz. Now, L square operator we have already seen. L square is minus h cross square d by d theta sin theta d by d theta. There is a 1 over sin theta sitting around here, plus 1 over sin square theta d2 by d phi square, which I can write as minus h cross square 1 over sin theta d by d theta of sin theta d by d theta plus Lz square over sin square theta. And if I want to find the simultaneous eigenfunctions, I got to do L square, whatever those eigenfunctions are, let me call them P theta is equal to lambda P theta. You may wonder why I wrote P theta. That is because I already know the Lz eigenfunctions, and those are e raised to I m phi, and since these are simultaneous eigenfunctions of L square and Lz, there cannot be any phi term in P. If it were there, then Lz would operate on it. So, this P would depend only on theta, right. So, this is because L square and Lz have common eigenfunctions. So, this implies immediately that P cannot have any phi dependence. Now, the way one solves this equation is by writing P theta, expands it in terms of cosine of theta and its powers I, some coefficient C I. We are not going to do that. I will just state the result, and that is that these functions, when we calculate P theta equals lambda P theta, lambda value comes out to be L plus 1 h cross square. Now, and P theta are different functions. One of the functions is P theta equals 1, corresponding L will be 0. P theta equals cosine of theta, corresponding L is 1. Let us check the second case. First case is very easy to check because it is 1, so L square gives you 0. L square operator is minus h cross square 1 over sin theta d over d theta sin theta d over d theta plus Lz square over sin square theta, when this operates on cosine of theta, what do I get? The first one gives me 0, this term operating on this gives me 0, and the second term is going to give me minus h cross square 1 over sin theta d over d theta. Inside I get, when I multiply sin theta with the derivative of cosine theta, I am going to get minus sin square theta, and this leads to immediately plus h cross square 1 over sin theta times 2 sin theta cosine of theta, and that gives you 2 h cross square cosine of theta, which is nothing but 1 plus 1 h cross square cosine theta. So, cosine theta is an eigenfunction with L being 1. What is found is that when L square times this p theta is equal to L plus 1 h cross square p theta, then the value of m is restricted to, for a given L, to being from minus L to plus L in steps of 1. So, m comes out to be minus L plus 1, minus L plus 2, so on 0, 1 all the way up to L. And these eigenfunctions are going to be labeled and they have a name. L square, they are called spherical harmonics, they depend both on L and m. Theta and phi is going to be equal to L plus 1 h cross square y Lm theta and phi, and as I said earlier, the phi dependence we know because of these functions being simultaneous eigenfunctions of Lz also. So, I have L square Lm can be broken into p Lm that depends only on theta, but does depend on L and m both, e raised to I m phi is equal to L plus 1 h cross square p Lm theta only e raised to I m phi, and Lz operating on y Lm theta and phi is nothing but Lz operating on p Lm theta e raised to I m phi, and that gives me m h cross y Lm theta and phi. M for a y Lm theta and phi, m is restricted between L and minus L in steps of 1. So, m can be equal to minus L plus 1, so on up to 0, 1, 2, L minus 1 and L. So, this is how the eigenfunctions are given. I have not given you details, I have just given you 2 eigenfunctions, right, and that is what it is. This is where we stop. Other things take us into mathematics of how to determine these eigenfunctions. If you want to know the technical terms, the eigenfunctions come out to be the associated Legendre polynomials PLMs multiplied by these e raised to I m phi's, but the YLMs, these have a name, these are known as spherical harmonics. So, I have given you 2 eigenfunctions, others I can keep giving and ask you to check what they are like. And once you then go to the Hamiltonian for spherically symmetric systems, this can be written as H equals minus h cross square over 2 m r square partial with respect to r square partial with respect to r plus L square over 2 m r square plus V r. And since the eigenfunctions psi are going to be simultaneous eigenfunctions of the angular momentum operator. So, I can easily write that L square psi is going to be equal to L plus 1 h cross square psi. Why? Because psi are common eigen functions for both h and L square. So, that automatically implies this, and therefore, the Hamiltonian can be written as minus h cross square over 2 m r square partial with respect to r square partial with respect to r plus L plus 1 h cross square over 2 the mass r square plus V r for all eigenfunctions for spherically symmetric systems. So, this is common. V r could be anything, this term would be the same. So, let me write this. This term in the Hamiltonian will be the same for all V r, and those YLMs will also be the same for all V r's. This we will see in more detail in the next lecture, but this is how the Hamiltonian gets simplified, and what you see in this is that now we are expected to solve only a differential equation which is for r. The theta phi components have been taken care of. So, because of spherical symmetry, the problem gets simplified. Now, before I leave this, we can consider, because of Lz, suppose there is a particle moving in xy plane. So, particle moving in xy plane with its distance fixed from the center. So, for example, it could be a rod with a mass here and moving around with no potential. So, let us take V to be 0. Find the energies. So, the Hamiltonian for the system is nothing but the angular momentum square divided by 2 m r square, where r is fixed, r is, let us say, the radius is given to be r, and angular momentum is only z angular momentum. Because V is 0, angular momentum is conserved. So, I can write it like this, and this is going to be minus h cross square over 2 m r square d 2 by d phi square. That is the Hamiltonian, and because V is fixed, the eigenfunctions of h and Lz are common. So, you can immediately write that the energy is going to be h cross square mz, I am writing mz to differentiate from mass, over 2 mr mz square or 2r square. But you can also do it if you want by solving the equation. So, I have minus h cross square over 2 mr square operating on psi equals E psi, which gives me psi, this is d 2 by d phi square, d 2 psi by d phi square plus h cross square E over 2 m r is fixed, psi equals 0. So, immediately you get psi equals e raised to square root of h cross square E over 2 m r square phi, and h cross square E over 2 m r square square root should be equal to m z or times 2 pi should be equal to mz because of the uniqueness of the wave function, and therefore, you get your answer. So, you can see this also directly by writing the Hamiltonian times psi equals E psi. Hamiltonian we have written as minus h cross square over 2 m, radius is fixed r square, d 2 psi over d phi square equals E psi. So, I am going to have d 2 psi over d phi square plus 2 m r square over h cross square E psi equals 0. So, the solution is going to be psi equals e raised to I square root of 2 m r square over h cross square E times phi. This is the solution. And if I demand again for the unique value of psi, psi phi plus 2 pi should be equal to psi phi, it immediately gives me that 2 m r square over h cross square E square root should be equal to mz, where mz is equal to 0 plus minus 1 and so on, and therefore, E comes out to be h cross square mz square over 2 m r square as obtained earlier. So, you see this having a thought about simultaneity of the eigenfunctions also gives me a tool to simplify my solutions. What we have done in this lecture, I will just conclude now, that we looked at angular momentum operator in detail. We have found that only L square and one component of L can have common eigenfunctions. We have also found that for convenience Lz is chosen to be the component and eigenvalues come out to be m h cross, m equals 0 plus minus 1 and so on. Then we also found that L square eigen values are L, L plus 1 h cross square, and what I did not write there is L is 0, 1 and so on. This is greater than or equal to 0, and L square and Lz have common eigenfunctions that we have already decided, and this h L square being 0 and h Lz being 0 simplifies the Schrodinger equation for spherically symmetric systems. What I would also just comment with respect to the point for the eigenvalues for Lz, and I am encircling it here, is that the eigen values for Lx and Ly operators will also be the same if we decide to solve for them, except that the eigenfunctions are going to be slightly more complicated, because the direction should not really matter. Lx, Ly and Lz for spherically symmetric systems are all the same. We choose Lz for convenience because the wave function becomes very convenient. We could have chosen to work in terms of Lx or Ly and L square instead also with the same results.